Hello, everyone. Today our topic is polynomial functions and their graphs. So what we are going to learn, what is polynomial and how to graph polynomials. We're going to start with definition. What is polynomial? So polynomial of degree n is defined next way. P of x equals an x to the power of n, an minus 1 multiplied by x to the power of n minus 1, plus lots of other terms, and then a1 x and plus a0. So here you can have many terms or no terms. What is important? That n is integer, not integer, actually a whole number. I would say that the last term actually has x to the power of 0, this a0. So that's why I'm writing it as a whole number. But you can kind of consider the just natural number like 1, 2, 3, because the first power of x here is 1, and then going 2, and then 3, and then until you reach power of n. What else? The coefficient an is not equal to 0. So the first coefficient is not equal to 0. You would say, oh, why first coefficient is not equal to 0? Any polynomial is supposed to have a first coefficient, right? So we are going to consider a degree of polynomial, the power of x of this first coefficient, considering that the greatest degree is sitting at the front of the polynomial. Okay, what are other numbers like an minus 1, an minus 2, and a1 eventually, and a0? Well, they're just coefficients, and I'm going to write down coefficients. In our case, they're going to be real numbers. A0 is going to be called a constant term. Okay, an, the very first one, this one is called a leading term. And oh, no, not leading term, leading coefficient, sorry. Leading term is going to be the whole product of them. An over multiplied by xn, leading term. Okay, well, a simple example of polynomial. P of x, sorry, somehow I press eraser suddenly. 2x cubed plus 2x plus 5. Typical polynomial. What is degree of this polynomial? Degree n equals 3. The highest power of x, it's degree. Okay, like leading term. It's 2x cubed. Leading coefficient is not a, I would say 3 equals 2. What else? Constant term. In our case, a0 equals what? 5. I'll come over here. I'm going to write it like this. A0 equals 5. Okay, that's what we have here. So what are graphs of basic polynomials? Again, we already know them, but just for a little review. Some basic graphs. Graph number 1, f of x equals x. That's a polynomial of first degree. The leading coefficient is equal to 1. Leading term is equal to just 1x. It's going to look like bisector of x and the first quadrant. And I'm just going to very quickly draw that. Okay, It's one here, one here. Number two, sorry. Number two, f of x equals x squared. Well, we know that it's going to graph for us a parabola. Something like this. 1, 1. That's a polynomial of second degree. And the leading term is x squared, and the leading coefficient is equal to 1, right? I'm going to do just very, very basic graphs. We are going to learn how to graph something more complicated a little bit later. Next graph is a cubic parabola. Label the numbers here, and then I will give you the equation of x equals x cubed. And the next one, number 4, I'm just doing like very basic powers. If you consider f of x equals x to the power of 4, that's a basic parabola of 4th degree. Looks like a square parabola, but a little bit more like, I would say, fat, more square. Like this one is more curved over here. This one is going to be more squared. Let me just draw it more squared so you will kind of feel the difference. Well, I want to kind of draw one transformation to show you how transformation is going to look. Though we did transformations already, and you probably know how everything is working. But for example, if you add 2 to this polynomial of 4th degree, you're just going to take the whole picture and shift it 2 units up, right? You draw the picture. So 2 units up somewhere here, and that's going to be a similar shape of 4th degree polynomial. So it's 1 here, x here, and y over here. Okay, so what we need to know about polynomials. First thing we'll need to know is end behavior. And here. What is end behavior? Well, how the polynomial behaves if you go at infinity in x direction. For example, over here, when x goes to infinity, y, which is f of x, will go to infinity same way, right? So you can write down x goes to infinity, y goes to infinity, right? On this side, when x goes to negative infinity, like becoming a very large negative number, you know, because y is actually equals to x, we are going to write down that y goes to negative infinity. What is going to happen to parabola? We see that the difference is that both ends go to positive infinity. So x goes to positive negative infinity, y goes to positive infinity only. Both y's are becoming infinitely big. For cubic parabola, 1 positive and 1 negative. So you can write down that when x goes to positive infinity, y goes to positive infinity. If x goes to negative infinity, y goes to negative infinity. What we see, guys, mostly if your polynomial has a odd degree, like 3 or 1, infinities are going to be like corresponding to axis, right? If it has even degree, it's going to go like to positive infinity only. But also it's going to depend a little bit on coefficient in front of this greatest term. Let me kind of show you how to deal with end behavior if you have anything more complicated. I'm going to go to example of polynomial of 4th degree. 2x to the power of 4 plus 3x plus 1. How do we figure out end behavior here? I'm going to consider x equals 10. Almost infinity, right? Looks like 10 is not infinity, right? But let's consider 10. We are going to see what is going to be the difference between terms when x goes even to 10, not talking about infinity, which is much larger. How polynomial is going to look? I'm going to calculate polynomial at this point, polynomial at 10. Minus 2, 10 to the power of 4 plus 3 multiplied by 10 plus 1. I'm going to multiply each term. So here I have 10 to the power of 4, it's 10,000, right? So it's going to be minus 20,000. Plus this term is 30, and plus the last term is 1. You see that the leading term is much larger than two other terms, right? Why does it happen? Well, because you are raising to the power. Imagine that you kind of take a number 1 million and square it. And that's going to be much larger number than 1 million itself, right? So normally, guys, what is going to be the result of this addition is going to be defined mostly by leading term. Leading term actually defines what happens at infinity, because these two terms are making a very small difference to leading term. So when you want to find end behavior of your function, you are going to look at leading term only. You're going to look at this leading term and decide like where it goes at infinity. Well, we see that in this case, when x is becoming large or like close to infinity, just imagine like 100 here, y, which is the result of this expression, is going to go to negative infinity, right? Negative infinity happens why? Because there is a minus in front of the coefficient. What is going to happen when x goes to negative infinity? Well, if you plug in, my leading coefficient is minus 2x to the power of 4. If you plug in over here negative infinity, or a large number, let's plug in negative 10 here, you are going to get minus 2, negative 10 to the power of 4, which is still going to give you minus 20,000. Just why does it happen? Because the fourth power actually eliminates a minus. So minus is not going to change anything here. So y will still go to negative infinity. You see? So normally what we are going to do to find the end behavior, we are going to look at leading term and try to figure out what happens to this leading term when x goes either to positive or negative infinity. Later, it's going to help us to build our graph. So what does it mean? How is going to help us to build our graph? Well, I'm going to do a little graph over here, but it's not going to be actually a precise graph. It's going to be very approximate graph. I'm going to do the graph only at like infinity. So what I have, when x is large, positive infinity, y goes to negative infinity. Positive infinity is somewhere here, right? Somewhere here. So y goes to negative infinity means that the graph behaves like this, going to negative infinity. Y here. And when x goes to negative infinity over here, y will go to negative infinity too, this direction. I don't know how fast it's going to go to negative infinity. It goes like this or like that, or, you know, maybe like this. But what I know that it will go down. What is going to happen in between? I really don't know. It can be something like this or like that. I don't really know. So the region around 0 will need the additional investigation. But what happens at infinity, we can decide using this reading coefficient. Okay, I'm going to ask you to check this function on your own. The function is polynomial equals 2x to the power of 5 plus 3x squared. I just want you to find the end behavior. I'm going to count to 5, but you can stop my video and try to solve it on your own. So 1, 2, 3, 4, 5. I'm going to start solving it. So I'm going to look at my leading term, and leading term is 2x to the power of 5. What is going to happen when x goes to positive infinity? Well, this will go to infinity multiplied by 2. It's going to cause that y will go to infinity. When x goes to negative infinity, this number is going to become negative, right? Just imagine minus 10 to the power of 5 is minus what? 100,000, minus 100,000 by 2 is going to be a negative number. So y will go to negative infinity. And my graph will go like this. Oh, sorry. Positive infinity here, negative infinity here, and something unknown in the middle. Okay? So imagine that we have y and x here. Okay, very good. Now, how do we find what happens in the middle? Well, we'll need to deal with like zeros of polynomials. So before we move to zeros of polynomials, I'm going to introduce a theorem. Real zeros of polynomials. Well, first, what is a zero of a polynomial? Zero of a polynomial, let's imagine that we have a parabola, something like this. The point where parabola intersects x-axis is called a zero of polynomial. Why? Well, because polynomial at this point, I'm going to label it x1, is going to be equal to 0, just because you plug it like the point over here and y is going to be equal to 0. P of x2 is also equal to 0. So x1 and x2 are zeros of this p of x polynomial. Well, we know that this is parabola, so it's a quadratic polynomial, the simplest one, right? You know that for parabola, every parabola can be represented as something like this. Well, if the leading coefficient is 1, then it's going to be x minus x1, x minus x2. You know that's factoring, right? And if x and x1 and x2 are kind of zeros, so solutions of this equation, then we can represent it like this. Well, actually, any polynomial will be represented like this. Just a number of parentheses is going to be larger. Let me write down the summary of this representation. Number one, if C is 0 of P of X, that means that P of C equals 0. Then, let me actually erase number one. I'm going to put just then, and put number one here. Then, number one, X equals C is a solution of P of X equals, P of X equals 0. Well, we kind of see this because it's just like, how do we find that? How do we define that it's 0? Well, we are plugging in over here. It's a solution of this equation. So, very obvious thing. Number two, that's less obvious. X minus C is a factor of P of X. Factor means that you can represent P of X as X minus C and multiplied by some other function like Q of X. Factor means that like something like this, that's a factor. So this is, for example, my X minus C, and this is kind of Q, my remaining function. Okay, I'm going to put it in parentheses. It's going to be more visible. What else? C is x-intercept of a graph of P of X. Well, how do we know this? Well, if you put C into your polynomial, it equals to 0, means that y is equal to 0. And that's actually the definition of intercept. So basically here, everything we are trying to say is absolutely same. We're just trying to unify it because sometimes we are going to label it this way, sometimes label it that way. So you should understand that all these statements mean same. And we even can kind of put over here 0, that's statement number 0. Okay, and they are equivalent. Equivalent means that you can kind of say this one, number one, and number one, from number one will follow 0 and 2 and 3. I'm going to put this equivalency and forgot to close parentheses here. So all these four statements are equivalent. Now, guys, let's see how it works and how we can do description of the polynomial using these rules and zeros. I'm going to consider example of a polynomial, and kind of that's going to be a simple one, but we are going to move to more complicated. So my first example is going to be P of X equals x squared plus x minus 6. That's just a parabola, right? What I'm going to do, guys, I'm going to factor this x minus 2, x plus 3. If you don't like to guess, you can find the roots. Remember that quadratic formula. And you just kind of open parentheses, and that minus 2 by 3 is equal to negative 6, and 3 minus 2 is equal to 1. What we have? Well, first, x equals 2 and x equals minus 3 solutions of P of X equals 0, right? Well, if you plug for example, 2 over here, you obviously are going to get 0 just because this factor is 0, right? Then we see that x minus 2 and x plus 3, I'm going to write it down like this, x minus 3 factors. Well, you see, obviously there are factors because the whole expression is built out of these two factors, right? And the x equals 2 and x equals minus 3 are also intercepts. Well, let me label them correctly, x intercepts, because it can be y intercept. Okay, so what else? How do we use this? Well, we can use, so I'm not going to graph this one. You know how it's going to look like. I'm going to, maybe I'm going to graph it just very briefly. I'm going to graph this. I know that parabola is going to have branches up because this is positive, right? And behavior is positive infinity on both x and x positive and negative infinity. So end behavior. And we have like number 2 here. And sorry, number 2 here and number negative 3 here. And our parabola is going to look something like this, right? That's x, that's y, and behavior both go to infinity. Now, let's consider something more complicated, which is going to kind of actually use this zeros of polynomials. Example number 2, p of x. Imagine somebody already factored polynomial for us. It's not always going to be the case, but we're going to start with easy exercises where polynomial is factored already. So somebody factored polynomial for us, right? So how many intercepts we have? We have x equals negative 2, x equals 1, and x equals 3. They are solutions of this, and this parenthesis. So they are zeros. And at the same time, intercepts. Well, let me label x intercepts. Okay. How they can be helpful to us? Remember, I was kind of explaining the test point method, and I was using polynomials. Let me graph actually these points on my number line and try to kind of use intervals to figure out like how my polynomial is going to look. For example, I'm going to use one test point to the left of negative 2. I'm going to use x equals negative 3. I know that if I plug in negative 3 into my first parenthesis, I'm going to have negative 3 plus 2 negative number, right? The second parenthesis is minus 3 minus 1, also negative number. And the last one is going to be minus 3, also negative number. So in total, I'm going to have final number negative. I'm going to put here minus. What is going to happen here between 2 and 1? Well, my favorite number is 0. I'm going to check it. And I'm going to have plus for first parenthesis, minus for second, and minus for third. It likes to make something what I'm not asking about. So plus minus minus is going to give me a plus, right? So I'm going to have plus over here. So my expression is going to be positive. I know that it cannot become suddenly negative on this interval just because to become negative, it's supposed to cross actually x-axis and have 0 here, right? But I don't know that there are no zeros here. Okay, next one, x equals, well, from 1 to 3, the good number is 2, right? 2 plus 2 is positive number. 2 minus 1 is also positive number, and 2 minus 3 is a negative number, and I'm going to have in total minus, plus, plus, minus. And the last one, I'm going to use x equals 4. And 4 is going to give me plus, plus, and plus for all 3 parentheses. Plus, plus, and plus, right? So my final answer is plus. How it's going to help me? Well, it's going to help me next way. If I graph the polynomial, I'm going to draw a number line, actually, real number line, and put my real numbers like minus 2 here, 1 here, and 3 here. I know that before minus 2, my polynomial is negative. So I'm going to put some negative expression here. At 2 is becoming positive, and that's positive until 1. So I'm going to do something like this. From 1, it's becoming negative again and going to be negative until 3. And after 3, it's going to become positive and goes forever positive. How do I know how far I should go here or here? I actually don't know, guys. That's my assumption that it goes up and down that far. It can go much further. It can be something like this, for example, and something like this. I don't know, but at least I got some picture of this polynomial, and I think that's going to be good for us to even have a picture like this. Now let's consider maybe another example which is not going to be factored, and we are going to be factoring the polynomial, more complicated example. So example number 3, polynomial is equal x cubed minus 2x squared minus 3x. Step number 1, we'll need to know this zeros. To find out zeros, we'll need to factor polynomial. And I'm going to start factoring it. From first, second, and third term, I'm going to take away x outside of parentheses. I'm going to have x, and here, instead of x cubed, I'm going to have square, right? Instead of square, I'm going to have the first power, and instead of just 3 minus 3x, I'm going to have just minus 3. Well, I'm going to continue factoring, and my factoring of the binomial is going to give me x minus 3 and x plus 1. What do you think? Minus 3 by 1 is negative 3. And minus 3 plus 1 is actually minus 2, right? So works good. I mean, guessing here is working good. Now I'm going to kind of find my intervals where my polynomial is positive or negative. So I'm going to start with x equals 0. And this is x equals 0, right? This one is going to give me x equals 3. So that's 3. And this one is going to give me x equals negative 1. Negative 1 is over here. I put them on scale because I want to actually use this signs when I graph the polynomial. So what do I have, guys? Well, let's consider numbers to the left of negative 1, like negative 2. Negative 2, negative 2, and negative 2. All are going to produce negative expressions, minus, minus, minus. So in total, I'm going to have minus. Between negative 1 and 0, negative 1 and 0, well, I can use x equals negative 0.5. Negative 0.5 is minus. Here is minus. And here actually is going to give me plus. So all 3 multiplied are going to give me plus because 2 minuses are going to give me plus. From 0 to 3, I'm going to use x equals, I don't know, let's use 2. Then I have positive for the first parenthesis. 2 minus 3 is negative, and 2 plus 1 is positive. So in total, plus minus plus is going to give me minus, and I'm going to put minus here. The last point I'm going to consider maybe something like to the right of 3, like let's consider 10. So 10, 10, and 10 everywhere is going to give me a bunch of pluses. So the final is plus. And I'm ready to graph my polynomial. Guys, I don't want to graph it on a coordinate plane. I'm just going to graph it right over here. So it's negative here, then it's shortly positive, then it's negative again, and then it's positive. Let's check our end behavior looking at my greatest, my leading term. When x goes to negative infinity, we're going to see that when we cube it, negative infinity, it's like 3 minus s cubed. Y will go to negative infinity too, and we kind of see it over here. If we draw y-axis here, we're going to get it. It's negative infinity. Over here, guys, when x goes to positive infinity over here, we are going to see that y will go to positive infinity too, just because infinity cubed, it's still positive infinity. Everything works perfectly. So we graph the next one, and maybe, guys, I want to ask you to graph something on your own. Let me write down the problem. And again, I'm going to count to 5, and you will do the graph. Maybe I'm going to ask you to graph 2 graphs. Self. Number 1. I'm going to give you a factored polynomial, okay? Factoring is not easy task. And number two, well, for all this, I want you to find the zeros and find how polynomial behaves on intervals between zeros, okay? And then try to approximately graph how polynomial is going to look. Again, the graph is not going to be very precise, but maybe it's some information still good. Let me, sorry, 2x minus 3. This 2 doesn't look like 2x minus 3. Okay, so there are two polynomials to graph, and I want you to spend like 5-10 minutes maybe. Again, no one is asking you to make a very precise graph, just like what you can, the best you can do. Okay, so I'm going to count to 5 and do solutions, because you know that you can always stop my videos. So solutions 1, 2, 3, 4, 5. I'm going to start with my first problem. In the first problem, my polynomial has only two factors actually, right? X squared and x minus 2 cubed. My zeros, x equals 0, right? And if I set up this to 0, it's going to be x equals 2. So I'm going to have a number line and only two zeros, 0, and let's make it 2 over here, which is going to be very easy to check intervals, right? So for example, I start to the left of 0. I'm checking x equals -1. -1 for the square is going to give me positive, because square is always positive. -1 here is going to give me -3. Cubed is going to be negative. Remember that if you multiply minus 3 times, you are going to get the minus. So here I'm going to get minus. Next, the interval between 0 and 2, I'm going to use x equals 1. So 1 here is still positive instead of square. And 1 minus 2 is still negative. Still negative means that we are going to have minus. Well, again, 1 minus 2 is -1. If you cube it, it's still going to leave you with minus. So you're going to get a minus again. And the last one is going to be interval from 2 to infinity. I'm going to use point x equals 3, which is to the right of 2. So 3 squared is still positive. Looks like the square doesn't change at all, right? And 3 minus 2 is 1. If you cube it, you are going to have plus again. So we are going to have plus here. Now, how the picture is going to look? Well, you see we have two minuses. What does it mean? That the function has a 0 here, so it goes through the axis, but it does not actually cross it. So it comes to x-axis, but it stays negative after that. So it goes back down, and at this 0, it crossing x-axis because it changes from minus to plus. You have minus here and plus here, means that it intersects it. Here, it's just touching. Okay, so that's our graph. And for the next problem, let me try the next problem. P of x equals x plus 2, x plus 1 squared, and 2x minus 3. So again, I'm going to find zeros. And we remember that zeros are going to be solutions of little factors. Okay, let me. So my first factor, x plus 2, is going to give solution -2. Second factor is x -1. And the third factor, 2x minus 3 equals 0, is going to give me a solution x equals 3 over 2. Not a very nice one, but still, like, why not? So we are going to have three possible, like, 3 intercepts, but 3 possible points where the graph is going to change direction. I'm going to graph them like -2, -1, -1 doesn't look like -1, and 3 over 2. I'll put it over here somewhere. Okay, So now we have 1, 2, 3, 4 intervals to check, and I'm going to start with x equals -3 to check interval from -infinity to 2 to -2. So -3 here will give me minus, right? -3 plus 2 is -1. -3 here will give me plus because it's squared, and -3 here is going to give me -2. So sorry, we have 2 minuses, 1 plus, total amount is plus. X between -1 and -2. Well, I don't know which one to use, but I'm going to use -1.5. -1.5 plus 2 is plus. Square is always plus, and -1.5 is going to give me -3 by multiplied by 2 minus 3 is still minus. I don't like the computer made a circle out of my parentheses, still minus. So we have plus plus and minus, which is going to give me minus here. Well, between -1 and 3/2, I'm going to use 0, and that's going to give me 2, 1, and -3, which is going to give me minus, right? I'm going to write down plus, plus, and minus. And the last one is from 3/2 and further to infinity, I'm going to use 5. So in all 3 cases, 5 is going to give me pluses, plus, and plus. I'm going to get plus. Well, 5 plus 2 is 7, 5 plus 1 is 6, squared still positive, and 5 multiplied by 2 is 10, minus 3 is going to be 7, still positive, right? So that's what I have. Well, I think I'll just graph it right over here. So we have plus, so something positive, and it crosses x-axis because it's becoming negative, right? Let me actually draw the line better. Not supposed to actually move my plus. So I'm going to over here at point -1 is just touching, right? Because it does not change the sign. It was negative and it's still negative. And then the next intercept, it will cross x-axis. Well, that's how the graph is going to look. If you wish, you can graph actually somewhere here like y-axis. And very nice to also check end behavior here and here. What is going to be the greatest power of x here? Well, the first is 1, 2, and 1 plus 2 is 3, plus 1 more is 4, right? And the coefficient is going to be positive. So that's the coefficient, the leading term is x to the power of 4. X to the power of 4 will go to positive infinity always because the power is positive, right? For x is going to positive and negative infinity. And that's what we see on the picture, right? Goes to positive infinity. Okay, that's all for today's lecture. And please do your homework. I know that the lecture is a little bit long. I want you to practice at least 3-4 graphs of polynomials, okay? And thank you and see you next class.